This is section 13.3, and this is our last example for the section. This is example number 5, and we have a vector field that we're considering f of xy, and we're going to first determine whether or not the vector field is conservative. So remember, we have our form of our vector, which is pq. So that means that p is equal to 3 plus 2 xy, and q is equal to x squared minus 3y squared. So that means that dp dy is 2x, and dq dx is 2x, and these are equal. So therefore, by our little test here, f of xy is conservative. That's good news. So this will be a lot easier. So for part B, we're going to come up with a potential function. Remember that you just use a little bit of intuition here and try to come up with, some ideas and test whether or not they work. We know that the partial, if it is truly conservative, then the partial derivative of f with respect to x is going to be 3 plus 2xy, and the partial derivative with respect to f of y is x squared minus 3y squared. So let's take a look at our first one. Basically, let's just think about this. Forget y, let y be a number. So the antiderivative of that first one with respect to x is going to be 3x plus x squared y. In other words, if we take the antiderivative, if we take the derivative with respect to x, we get 3 plus 2xy. If we take the derivative with respect to y, we just get 2xy. If we take the derivative with respect to y, we get just x squared, which does show up here. That's good news. But we also have this piece that we need. So if we tack on a minus y cubed, now we have not changed the derivative with respect to x. So that's still okay, but now we have accounted for the derivative with respect to y. So again, if we take the derivative with respect to y, we get x squared, and then we get negative 3y squared. Don't forget, we may have to add a number to that, but when we use the fundamental theorem, that doesn't matter. Okay, for part C, we're going to calculate the line integral, f dotted with dr, and we have r of t given to us as e to the t sine t times vector I plus e to the t cosine t times vector j. And we're given the information that t is going to go from 0 to pi. And we're going to use the fundamental theorem here because it's going to be much faster. So remember, the fundamental theorem says that this line integral that we now have called the gradient f dotted with dr is equal to the potential function that we came up with of r of pi minus the potential function of r of 0. So off to the side here, let's do r of pi and r of 0. So r of pi is going to be, let's see, e to the pi times sine of pi, which is just 0, and then e to the pi times cosine of pi, which is negative 1. So we get negative e to the pi, and r of 0, we get e to the 0 times sine of 0, which is going to be 0, and then what we get is e to the 0 times cosine of 0. Those are both 1. So there we have it. We have both r of pi and then r of 0. All right, so then that gives us f of, so r of pi was 0 and negative e to the pi. Remember, what we're getting then is our x value, which is 0, and our y value, which is negative e to the pi, and then subtracted by f of 0, 1. And so what we're going to do now is we're going to plug this back into our original, into our potential function that we created. So the potential function that we created, I will write right here. So we have our potential function f of xy was 3x plus x squared y minus y cubed plus some constant c. All right, so what we have then is f of 0, negative e to the pi. So we're going to plug in 0 for x right here, and then we're going to plug in negative e to the pi for y here and here. So we get 0 and 0, and then we get minus negative e to the pi cubed. That's our first one, okay? And then we have 0 for x again, and 1 for y this time. So again, 0, 0, 1, 1. That gives us just negative 1. So what we get for an answer is e to the 3 pi plus 1. Okay, that is section 13.3.